In this lecture, let's look at the electric field formed from a point charge. We know that from Coulomb's law, magnitude of force between source charge and test charge is as follows. It is 1 over 4 pi epsilon naught, or this entire constant also equals to Coulomb's constant, then times magnitude of source charge times magnitude of test charge divided by the distance separated by the source and the test charges squared. Then using what we learned from the previous lecture, magnitude of electric field caused by the source charge, Q, would be absolute of the force on Q prime, the test charge, divided by the test charge. So we substitute Coulomb's law into the force on Q prime, then divide this by magnitude of Q prime. Then we get this. The electric field caused by the source charge is 1 over 4 pi epsilon naught times magnitude of the source charge divided by distance squared. Note that for point charges, for the force and electric field, they are proportional to 1 over distance squared. So the further away the test charge is, the smaller in magnitude the force and the electric field is. How about the direction of the electric field? We know that the electric field is created by the source charge. So again, the direction is only dependent on the source charge. When the source charge is positive, then the electric field will be pointing away from the charge. And when the source charge is negative, then the electric field will be pointing toward the negative charge, as shown in the figures below. For the figure on the left, we have a positive source charge, so the electric field are pointing away, and the figure on the right, we have a negative source charge, so the electric fields are pointing toward the negative source charge. Electric field is defined at every point in space. So even though in the figures there are only a few arrows, but the electric field is defined at every point, even if we don't put a test charge around the source charge. When the source charge is a point charge, then we can use this equation. The electric field equals 1 over 4 pi epsilon naught times the source charge divided by the distance squared, where r is the distance between the source charge to point P. And r hat is the unit vector pointing from Q to P. And just a quick recap, unit vector is a vector that has magnitude of 1. So the important information it gives is the direction. So again, from this formula, we can see again, when we have a positive source charge, the electric field will be pointing away because the r hat we define is the unit vector pointing from the source charge to another point, P. So on the other hand, when we have a negative source charge, the electric field will be pointing in this direction toward the source charge. Let's look at this example. A negative 1 nanocoulomb charged particle is located at the origin. Points 1, 2, and 3 have xy coordinates of 1 and 0 centimeters, 0 and 1, and 1 and 1 centimeters. Determine the electric field at this point, then show the vectors on the electric field diagram. So here's a sketch of the problem. I have a negative 1 nanocoulomb charge at the origin, and my point 1 is at 1, 0. Point 2 is at 0, 1, and point 3 is at 1, 1. Let's find the electric field at each point. Let's first determine the direction of the electric field. Since the source charge is negative, so the electric field would be pointing toward the charge. So the electric field at point 1, it will be pointing toward the left, toward the source charge. And at point 2, it will also be pointing toward the source charge. And since point 2 is directly above, so the field will be pointing downward. And at point 3, it points toward the source charge, so it will be pointing at a 45 degrees angle below the negative x-axis. Now let's determine the magnitude of the electric field. Let's start with point 1. The electric field is the constant 1 over 4 pi epsilon naught times the source charge divided by the distance to the point squared times r hat. The constant in front is also equals to Coulomb's constant, 8.99 times 10 to the power of 9. And the charge is negative 1 nanocoulombs, which is negative 10 to the power of negative 9 coulombs. And the distance is 1 centimeters. So denominator is 0.01 squared. And r hat is the unit vector pointing from the source charge to point 1. That is in the positive x direction. So it's I hat. And we get negative 9 times 10 to the power of 4. So it's pointing in the negative x direction. And the unit is newtons divided by coulombs. How about point 2? The electric field at point 2 would be 1 over 4 pi epsilon naught times the source charge divided by R2 squared in r hat. R2 is also 1 centimeters, so it has the same magnitude as E1. So this equals negative, since the source charge is negative, of 9 times 10 to the power of 4, and r hat in this case is j hat, because the unit vector from the source charge to point 2 is in the positive y direction. Then with a negative sign in front, the electric field is pointing in the negative y direction. And unit is newtons per coulomb. And lastly, point 3. The electric field equals 1 over 4 pi epsilon naught times source charge divided by R3 squared, then times r hat. R3 is distance from the origin to 1, 1, the coordinates 1, 1. So we need to find the distance. So to find the distance R3, we can use the Pythagorean's theorem. Square root of 0.01 squared plus 0.01 squared. And we get 0.0141 meters. So we substitute the constants and the source charge into the equation. We get E3 is negative 4.5 times 10 to the power of 4, and the direction is R3 hat. Unit is newtons divided by coulombs. We can also rewrite this in xy components. So E3 is negative 4.5 times 10 to the power of 4 times cosine of 45, and that is the x component. Then minus 4.5, the magnitude, times 10 to the power of 4 times sine of 45, and that is the y component. And we get negative 3.2 times 10 to the power of 4 I hat minus 3.2 times 10 to the power of 4 j hat. So that is the electric field at point 3. And that is the end of the lecture. Since the electric field is also a vector, so we also have to talk about the superposition. In the next lecture, let's talk about superposition of electric field.